I'm Dr. Wes Hines. I'm the Nuclear Engineering Department head here at the University of Tennessee. And welcome to our graduate colloquium program. Today, we're very lucky. We have Don Hollenbach. He has, Dan, I forgot to ask you. I know your PhD came from the University of Tennessee in 1992, and I know you have a bachelor's and master's in nuclear. Were all three of your degrees from UT, or did you get some of your degrees elsewhere?
No, my BS was from North Carolina State University, and my master's was from the University of Washington in Seattle.
Wow. Okay, so quite a variety there.
I'm a vagabond. I wander a lot.
Oh, so he's been a licensed nuclear engineer since 1988 and has over 35 years nuclear engineering expertise with over 25 years related to criticality safety at DOE facilities. From 2011 through present, he's worked as a senior criticality safety engineer at the uranium processing facility. It's out at Y12. His primary function is design analysis and calculations and critical safety evaluations, analyst and reviewer. From 92 to 2011, he was writing computer codes, teaching and doing criticality analysis for Oak Ridge National Lab. He wrote and maintained Keno 6 and several other codes in the scale code system. His experience includes modeling systems using both scale and MCMP, providing support for scale code system, modeling experiments using MCMP that were used for the validation program at the Yucca Mountain project, using Tsunami to help design critical experiments, and modeling systems using MCMP for the use by the Nuclear Materials Detection and Characterization Group. Dan, welcome.
Thank you. Today I've got an interesting discussion with you. Let's see. I need to figure out how to share my screen again. There it is. And slideshow. Come on. I lost where to do this.
And maybe all the way to the left there where, yeah, you need to maximize. That's one thing.
There it is.
Maybe the thing that over the left. There you go. Great. Looks perfect.
It's just slow. Okay. Well, today we're going to talk about the possibility of a reactor down in the Earth core. This is a completely natural occurring reactor. It doesn't involve anything like mole people powering their civilization. What we just theorized is that all of the uranium came into the core due to gravitational forces. Currently, there are a lot of heat sources theorized in the Earth. Latent heat diffusion as the core cools, radioactive decay, internal friction from rotation. The problem with all of these things is they're all steady state and decreasing power sources. But if you look at the Earth's history, you'll find that it looks like, because of volcanic activity, geometric reversals, plate tectonics, that we actually have a varying power source down deep in the Earth. And the only one I can think of would be cycling on and off reactors. Now, this is not a new idea. Over 60 years ago, a naturally occurring reactor was found on the Earth's surface in Oklo, Africa. It theorized it started about 2 billion years ago. Now, this was more of a thermal reactor. It cycled on and off with the rainy seasons. When water got in there, it started up and it operated while it was wet, and then it shut down when it was during the dry season. This was actually theorized in the 60s by Dr. Kuroda. And then in 72, it was discovered. And now that they've looked for it, they found many other sites that also contain fission product. So a natural occurring reactor has been shown to occur on the surface of the Earth. What we're going to do here is talk about the theory of it occurring deep inside the Earth. That's why it's called a deep Earth reactor. And possibly around the inner core. Now, the depth of the reactor is going to really depend on a balance of forces. You have gravitational forces, obviously drawing it in, but you also have rotational forces as the Earth spins, pushing it out. So it won't be in the exact center, but it'll be somewhere in a ring. We hypothesize somewhere in the inner core. If you look at uranium enrichment, right now it's 0.78% U-235. Well, geophysicists believe the Earth is about 4.5 billion years ago. So if you back calculate it to 4.5 billion years ago, it would have a U-235 weight percent of about 23.3, which is more than enough to power a self-sustained reactor. You only need about 7 weight percent for a self-sustained fast fission breeder reactor. So we're assuming large quantities of uranium can migrate into the core, and we have more than enough enrichment for this to occur. Also, if you look at the energy of fission, you get about 200 MeV per fission, and versus decay, which is really close to about 50 MeV. But it happens, obviously, decay happens at a steady and decreasing rate over a long time. Well, what we hypothesized is that the interior of the core of the Earth is similar to a highly reduced enstatite chondritic type meteor. This is a high metal content, and a large portion of the uranium and thorium from the meteor would have become parts of the Earth core, because uranium and thorium are very heavy relative to most other elements. And inside the core, there would be an inner subcore. And the interesting thing is, I just read an article just a little bit that geophysicists believe that indeed there is a small subcore inside of our inner core. So we're beginning to get more and more evidence that the Earth's, the interior of the Earth is much more complex than what was originally thought even 20 years ago. Now you got to keep in mind the Earth has got a radius of 6,378 kilometers at, I believe that's at the equator. So a 5-kilometer inner core is pretty small. They also believe we get about terrestrial heat flow about 45 terawatts, with 5 to 15 terawatts coming from the core. And they think a lot of this heat flow is coming from dissipation of power through the geodynamo that produces the Earth's magnetic field. Now, here are two competing theories about what the inside of the Earth looks like. We have a traditional geophysics model, which just has an upper mantle, a lower mantle, an inner core, or a fluid core, and then an inner core. And that's the standard nickel iron fluid core with silicates as your mantle, and the inner core would be nickel iron components. We think that the deep earth or nuclear reactor model has a much more complex. We have the same upper, lower, and fluid core, but the inner core is divided into more fine substrates. And I'm not going to go into this. This is geophysics, which is not my expertise. My expertise is nuclear. So we're going to discuss that. Well, if we assume an initial uranium mass in the core of about 2.1 times 10 to the 19th grams, this is what we get when we take part of just a portion of the uranium we feel would be available if the inner core is made out of enstitite chondritic type meteors. So we have a way that the uranium could have gotten there. Now you'll notice it's got a much higher density. That's because it's under a lot of pressure. And at the pressure in the inner core, uranium would have a density of about 36.8 grams per cubic centimeter versus what you see on Earth, which is about 19 grams per cubic centimeter. And again, the elements would separate out due to gravity and convection currents and the Earth's rotation. And if we just looked at not reactors, just decay, the uranium we had in there would have started about 4.5 billion years producing about 4.5 terawatts. And today it'd be producing about 0.8 terawatts. Now, what we're going to do is talk about how a reactor could work if there is indeed one in the inner of the core. And I believe the thoughts of a reactor in the core started out as just a strong suggestion, but I think it's at this point it's a reasonable hypothesis on which we can do a lot more work. But how it would work would be the power would not be steady state, it would be fluctuating. As uranium would accumulate, the power would increase and would be putting out heat. It would be producing lighter fission products and a lot of poisons. And as it accumulates that, the power would be decreasing. Lighter fission products and poisons would then migrate out of the reactor. Heavier actinides would aggregate due to gravity, and the power would go back up. So we would, in effect, have multiple, and by multiple, I mean thousands of smaller reactor regions that would exist independently and just be continuously cycling on and off. Okay, now how did we make this work? What we did was we set up a set of scale runs. Okay, let's go back and talk about helium formation first. Sorry. Helium-3 is what we're really looking at and provides us some evidence. Helium-3 to 4 ratios, particularly, the helium-3 to 4 ratio in the Earth is called Ra. That's the atmospheric ratio, is about 1.37 times 10 to the 6th. In the Earth, there are no natural processes that could produce helium-3 other than fission. On the other hand, helium-4 is produced by the decay of heavy elements and fission. So current geophysics theory is that the helium-3 that's present is there because it was there from the meteors. What we hypothesize is that helium that was in the reactor when it was, which was in the Earth when it formed, all migrated out of the Earth over the millions of years that the Earth was molten and being formed. So that all of the helium you see from the Earth was due to either fission or decay of the heavy elements. Now, what I did was I used the SAS2 analysis sequence and scale code package while I worked at ORNL. I had to modify it a little bit, but that's just bookkeeping, so I could run the longer time steps and keep the kind of data that I need, because we're talking about many, many gigabytes of data, which isn't a lot now, but back when I first did this in 2020 and or in 2000, and then in 2010, gigabytes of data was a lot of data to store. So I modified it to store only the stuff I needed. SAS2 calls origins, which calculates the isotopic concentrations, which are generated due to fission and decay. And unfortunately, it only does a 1D transport analysis. So I got to assume just one great big lump of of uranium. Did multiple things to make this thing work, but I was a pretty good programmer, so and I did it all on my own time, which produced some long days and weeks. So we assumed a huge homogeneous mass of uranium, assumed the isotopic concentrations were 4.5 billion years ago. We had to set the helium-3 absorption cross-section to 0 because there was no way to, otherwise it would all just turn into helium-4 eventually. Now, this isn't as bad as it sounds because actually when helium-3 absorbs a neutron, it goes to an excited state of helium-4, and most of it actually becomes, it ejects a proton and becomes tritium again, which is what helium-3, a lot of the helium-3 starts at. Tritium decays with, I believe, about a 12.5-year half-life. And we removed all the fission products so the reactor could operate, because the current state of the computer codes at the time I did this wouldn't allow us to migrate anything out of the core. Whatever was there had to stay there. We can do much better today. So I did this in million-year time steps, and I started, which went from 4.5 billion years ago to 1.5 billion years in the future. I also ran shorter time steps of 1,000, 10,000, 100,000 years to make certain that the million year was reasonable, and it showed absolutely no difference. They gave the same results. Calculated at 4 different steady state power densities, 0, 1 terawatt, 3 terawatts, and 5 terawatts. And I varied the start time of the reactor from 0 to 2 billion years to give the uranium time to migrate into the center of the Earth. And then I ran one additional cycle run and varied the power from 2 terawatts for 1 million years, and then 0 terawatts for another million years. And I just cycled it on and off to see if that made a difference, and it didn't. Steady state gives a good example. Now, the first thing I did was run it at 4 times the uranium loading I showed you before. And as you can see, it cycles for just fine. It's still working theoretically at today's standard. So we know with 4 times the power at 3 terawatts, it works great. But now I also I knew it worked then, so now I reduced it to the amount of uranium I specified earlier in the table, and ran it at the different time steps. And in each of these things, I then varied when I turned the reactor on. And as you can see, when I turned the reactor on was, you see a definite curve. The top blue one was I started it straight away. Then I started it 500 million years later, then 1 billion years later, 1.5 billion, and this is the just under or right at 2 billion years later. And if I started it any later, it decays to less than 7 weight percent U-235, and it won't start at all. So given this, we can see that the reactor would keep running at 1 terawatt theoretically for another 1.5 billion years. And this is the U-235 to uranium thorium ratio that we get, and you can see that it actually levels out right just above 7 weight percent. and just stays there. At that point in time, the amount of uranium being produced balances with the amount that's being burned. So it really is a fast breeder reactor with a very long lifetime. So we see at 1 terawatts, it works. At 3 terawatts, we can see that based on these curves, that it would not stay working today unless it started right at the 2 billion years ago. And again, it goes to the same exact, it goes around about somewhere between 7 and 8 weight percent, and just stays there and burns. And then finally we did, we did 5 terawatts, and 5 terawatts, regardless of what you do with the uranium loading we have, would not be operating today. If we increase the loading, indeed we could, it would still be operating today. Now, so that is what we just talked about with delayed startup times. Lets the reactor run longer, and it breeds the uranium. It breeds in U-235, Pu-239, and U-233, and we have to remove the fission products for this to work. Now we have some issues here, which would counter also some of the downside we saw about how long it could indeed run. We are running at 1 terawatt. With the amount of uranium we have a very, very small neutron flux in there, on the order of 1 million times less than what you see in a normal power reactor. And what this means is that anything other than U-235, most of it decays before it would fission. You can see thorium has a 14 billion year half-life, 238 almost 4.5 billion years, U-235 over 700 million years. But then if you go to 233 and Pu-239, that's not a whole lot of years. 159 million years or 24 million years is a lot of years to us, but to the Earth, it's a blink of the eye. So, you know, U-238 capturing a neutron and eventually coming to Pu-239, most of the Pu-239 in the time step of 1 billion years or of 1 million years, with the neutron flux level that we have, most of it decays back to 235, which we can then use. But the thorium, which goes to 233 when it absorbs the neutron, will eventually go back to thorium-229. So the increase in fissile material you would normally see from thorium being in the reactor, you don't see. Now, fission density was directly related to power. And what I'm saying here is exactly what I said. Power reactor is about 1 watt per cubic centimeter. The deep earth reactor at 1 terawatt is about 1 microwatt, about an order of 10 to the 6. And this is why we don't see a whole lot of fissions from Pu-239, and definitely not from U-233. But let's look at some evidence that this thing is actually working. The U-235 U-238 ratio will decay, or with decay, only falls below that for fission after 2 billion years. We already discussed that. Uranium enrichment stays actually closer to 7% than 6%, and and we have a very low reactor power level. and we've talked about this stuff. Now we're going to talk about helium production. And this is what I think actually provides a lot of evidence that this is really going on. Now you got to keep in mind, Ra is 1.37 times 10 to the minus 6. That's what we see on the Earth's atmosphere. And this is what we see when we look at what we see when we run these simulations. And that is helium 3 to 4 ratios steadily increasing. This is the 1 terawatt one. And by the time we come to Earth, we come to our present time, it's somewhere on the order of 12 to 13 RAs at 1 terawatt. This is average, or this is instantaneous power, or instantaneous helium 3 to 4 ratios in this one, and this is cumulative. So at present day reactors, about right here, you'd see it about helium 3 to 4 ratio is about 6. Instantaneous, you'd see about 12 to 13. At 3 terawatts, they go up dramatically. At end of life, we see it actually above 35 for the instantaneous, and we see it actually at about 8 for the cumulative. So we're seeing large differences in helium 3 to 4 ratios, and for 5 terawatts, they just go nuts. We can get them up to almost over 40 for 5 terawatts instantaneous, and over 20 for cumulative. Now, you need to keep this in mind, because what we see on Earth is from deep wells, we see huge swings in the helium 3 to helium 4 ratios, going from almost what you see in atmosphere up to, in some instances, 20 times what you would see in atmospheric ratios. So the only way you could do this, you could see this, is if we have, in my opinion, if you have a reactor and what you have is you're sampling from different areas in the core, in different volcanic regions that are pulling helium 3 or helium out of the wells. Okay, it says right here we see helium ratios up to 34 times atmospheric from deep mantle magma sources, which are generally around extinct or active volcanoes. Okay, helium is the second lightest element. It's a noble gas, so it does not react. So it has the highest chance of escaping from a reactor if there's one down in the core of the Earth. Helium 3 or hydrogen 3, which is tritium, is produced as a ternary fission products about once in every 10 to the 4th fission. So there's not a lot of it made, but when you talk about a huge amount of fission going on, that's still a lot of helium 3 being made. Helium 3 decay, or hydrogen 3 decays to helium 3 with about a 12.32 year half-life. And helium 3 has a very large NP reaction relative to capture, which means most of the helium 3 goes back to tritium when it absorbs a neutron. So, which is, if you thought about it, it's relatively obvious. Helium 3 to helium 4 ratios will increase over time as U-238 is consumed, because less helium 4 is being produced by decay, And it also increases as power increases because there's more helium-3 being produced per fission than there is helium-4 on average. And you saw helium-3 to 4 ratios go asymptotic as the reactor reached its end of life. I think that's just a artifact of the code and the fact that we have much less uranium. And the observed high helium-3 ratios, which are seen in many Hawaiian island volcanic lavas, and now it's being seen in other helium wells, which they're finding lots of helium now that they're drilling by extinct volcanoes. So again, another possibility that this is indeed true, that we could have a reactor down there. And as I said before, reactors would not be homogeneous or at any uniform power. They would vary with time and spatially and just cycle on and off. There would be thousands of small ones because anything happening 10 or 20 or certainly 100 meters away from a fission source will have absolutely no effect on it. The rate of helium U-235 fission is purely a function of the initial U-235-238 ratio, its power density, and its fission product removal rate. And the initial mass of uranium determines how long the system will survive and at what power. And if you have a large enough neutron flux, addition of thorium will indeed increase the system power in the lifetime. Now that's all we could do with the reactor or with the computer resources I had at the time. We have a lot better computer resources now. We could be doing some very detailed analyses of how these things might form and actually put in the driving effects that could cause uranium to migrate into the core. We could, that would be a fun project. If we looked at fission products, we could see if we could find some beryllium-10. The reason you'd look for that is it's got a 1.5 million year lifetime or half-life, and it's one of the lighter elements. So it is possible it could end up in deep mantle magma sources, such as what's found in ocean vents of the Hawaiian Islands. We could look for other noble gas ratios like neon or argon. We have, when I did this, we had no data on how much neon or argon would be produced in fission. There was just no economic reason to do that, so it was never measured. We could also look at measuring antineutrinos from deep within the Earth. We have some antineutrino detectors. To my knowledge today, they still don't have directional components associated with them. So all you're getting is what the antineutrinos coming from all directions at the same time. But there's a lot that could be done. And these are just some of the references I have. I'm now opening it up for questions. Does anybody have anything they'd like to ask?
Great, thank you, Dan. Yeah, I was thinking about the antineutrinos. I think we had someone come in and make a presentation kind of dealing with nuclear security and NSA and the antineutrinos. So that was going to be my question, but you got me right there on the last slide and mentioned it. You know, it seems like they have several detectors over in Europe, and they can use it somehow to detect, I guess mainly detect changes and maybe do a little bit of directionality. But if this is something that's been occurring steady state or fairly steady state over, let's say our lifetime or the last 30 years, then I think it would look steady state. So there's probably not much information you could try to glean or try to deduce from those huge detectors over there, is there?
The biggest anti-neutrino detector I knew of when I was doing this was in Japan. And I don't remember much about it, but I knew they started taking data and they were only getting, maybe 100 or 200 hits a year.
Yeah. Yeah. Okay, Robbie, do you have a question?
Yeah. You talked a lot about the helium-3, helium-4 ratio from volcanic activity and such, but is there any evidence of other fission products that you could use, to have more than one piece of suggestive evidence?
Well, like I said, you could look at the other noble gases, the neons and the argons, and see what kind of differences, what the spread of isotopes you get from those. But to my knowledge, nobody's ever done that.
Okay, thank you.
Yeah, so there's Charles Hughes put in our chat. He said CamLand,
That's it.
which is the liquid scintillation anti-neutrino detector, is a 1 kiloton detector located at the Kamioka Observatory in Japan. Results based on a live time of 749 days and presented in 2005 mark the first detection of geoneutrinos. I guess those are neutrinos that are made inside the Earth, I guess. I mean, that's what a geoneutrino is.
Yeah, those are from the reactors.
It says the total number of anti-neutrino events was 152. So it's about 2 years, 152, so 75 a year, something like that.
Yeah.
4.5 to 54.2 were geoneutrinos. This analysis put a 60 terawatt upper limit on the Earth's radiogenic power from thorium-232 and uranium-238. So that's interesting.
Yeah.
Okay, there's another one. I kind of jumped down a little bit, but let me go back up to the first question. It says, how did uranium and thorium come at the very beginning in the core of the Earth? Is there theory to support the mass and enrichment that would occur billions of years ago? I think you kind of started that when you said our enrichment now is 0.7%, but if you back that out, I don't know how far it went up to 28%. Is that the answer to that question?
Yeah, if you start at 0.7%, it's simple math. Just to 4.5 billion years ago, it was 23.3% U-235 because of the different decay rates. Y'all, any nuclear engineer should be able to do that math.
Well, maybe if they're from NC State, but I don't know about here at UT.
Ooh.
I'm just teasing.
That was a low dig.
No, that was a self dig. Yeah. So I have another one here. I haven't read it yet, but I'll read it. It seems that Jupiter has a wonderful exothermic reactor, and the Martian reactor died. Could we put inside the moon and compare it to terrestrial detectors?
Actually, I had similar thoughts.
Really?
Because if this could actually be instrumental in keeping our magnetic field going. And if it is, that would explain why Mars doesn't have one anymore. The reactor inside the core died.
Huh. There's another question. Said, have you looked at Oklo in Africa?
Yeah, that was the first thing that we discussed earlier. That was the first evidence that reactors are naturally occurring on the Earth. But that was a thermal reactor because it
Right.
needed the rainfall for it to work. It needed water, it needed hydrogen.
Yeah, it needs the moderator.
Yeah.
Has that changed any over the last, 50 years? Or I guess it was discovered in 72, I think you said,
Yes.
something like that. Yeah, so has that changed any over the last 50 years? I guess the only change might just be the amount of rainfall, and that might change it.
Well,
I'm just
it's not
wondering
gonna, it's not gonna
Itself
work.
out, or if it's keeping itself going.
No, it stopped about 1 billion years ago. It only worked for about 1 billion years, and then it burned out.
Okay, so it hasn't been active for 1 billion years.
Yeah, it operated from about 2 to 1 billion years ago.
Oh, how do they know it operated then?
They have fission products there,
Okay,
and it's got a much reduced. It's got a reduced U-235 weight percent.
wow. Very interesting. Okay, we have time for a few more questions. We have any additional questions? I don't see any in chat. Feel free to raise your hand. Okay, it doesn't look like we have any other questions. I found it really interesting. And, some of the things that I think are interesting is just the creativity it took to go back and think about, how to use the code to try to think of the different reactions that are important that would help prove or disprove this hypothesis, and that we have these codes that can do that. And then by the use of some of these codes, and then sampling of some of these wells around the volcanoes, again gives us some evidence that this may have occurred or may still be occurring. Anyway, very, very, very interesting. Last chance for questions. Okay. Well, thank you, Dan. I appreciate you putting this together for us and coming over and giving us some additional things to think about. And hope you have a great day. Thank you.
Well, you're welcome. I hope you have a great day also.
Okay. Bye-bye.
Bye.